Hello guys, welcome to the channel. I hope you all are doing good. So the question that we'll be solving today is search in a rotated array. So let's see what the question is asking. So it says there is an integer array num which is sorted in ascending order and with distinct values. So we have been given an array which is actually sorted in an increasing order. And prior to being passed to your function, the nums is rotated at an unknown pivot index such that the resulting array is nums k to nums n minus 1, and then from the pivot from where the element is rotated to k minus 1. The array is zero indexed, and uh, for example, they have given example like for example 0, 1, 2, 4, 5, 6, 7. If we rotate it from by index 3, this is the index 3, then the array becomes 4, 5, 6, 7, 0, 1, 4. Now given the array nums after the rotation and an integer target, we need to return the index of the target if it is present in that array, or we have to return -1 if it is not present in the array. And they have specified that we have to solve this in order of log and runtime complexity. So as we also discussed in my previous videos on binary search, so whenever a question that can be solved with binary search comes, then there are few information on the question itself that hints strongly that okay, this can be solved with binary search. The first hint is like the array is sorted. So we can see here the array here they have given is sorted in ascending order. That is one of the property of the data set or list where binary search can be applied, that the array needs to be sorted or monotonically increasing or decreasing. And they have usually they don't, like in interviews or something, you will not be told that you have to run it into order of login, but here they have specified that it needs to run in order of login. So this is actually clearly hinting that we'll have to use binary search for this problem. So to solve this problem, there are like couple of approaches, and I'll be discussing both of them. The runtime complexity would be more or less same, only the big O notation, but the way we write the code might differ. So let's now see how binary search can be used to solve this question. So let's say we have a array with following element 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, 9, 10, 11, 12, and let's say I rotate it by so if it was not rotated, then if this is an increasing sequence, then we would have simply applied binary search in this array, and then we would have got our answer, right? But now the question says that this has been rotated to from any index k. So for example, let's say I rotate it from this index k, so my new array will become, all these initial will be shift by k, so it will be 1, 2, 3, 4, 5, 6, and then these elements will come to the front, that is 8, 9, 10, 11, 12, right? So let's write the index here: 0, 1, 2, 3, 4, 5, 6, 7. Sorry, I didn't. Let's say we have a 7 also here. I missed 7. Anyway, 8, 9, 10, 11. Yeah. So you can see that we have rotated this array at a index that is 5, right? So uh, we have like this half of the array and this half of the array, and we need to find, let's say the target element is let's say we are looking for 10. Okay, so this is the target that we need to find in this data set. So now there are few observations that we need to find here that will actually help us in applying the binary search here. So first thing is, if somehow I'm able to find this pivot, this is pivot, the point from where the array is rotated. So if somehow I'm able to find this pivot element, then I can see that the element left to the pivot and element right to the pivot, including the pivot, both are itself one part is increase, both are in increasing sequence: 8, 9, 10, 11, 12, and from here also 1, 2, 3, 4, 5, 6, 7. So first thing is, like, if I am able to find the pivot here, then I'll simply have a two partition of the array and both will be monotonically increasing, and then I'll be able to apply simple binary search on this, right? For example, if I am able to find the pivot here, then my one of the array will be 8, 9, 10, 11, 12, and the other half of array will be 1, 2, 3, 4, 5, 6, 7. So if I'm able to find the pivot, then I can simply apply binary search for 10 in this half or in that half, and then it will give me answer. Here I'll not be able to find 10, so this part will give -1, and then this part will give like whatever the index of the 10. So this is actually the basic idea of solving this question, that we need to find the pivot element, right? Now, to find the pivot element, what we can do? So let's see what extra observation or extra information that we can have from this question that can help us to find the pivot. So if you remember, like we in the previous videos on binary search, we talked about the predicate thing, right? Like in any question that can be solved with binary search, there will be some elements which will satisfy some predicate, and then other elements which will not satisfy some predicate, and then we can eliminate the search space based on those predicate values. So let's see what is the predicate here. So if you notice it clearly, then every element to the left of the pivot, right, that will be always greater than the first element, and every element on the right of the pivot will be less than the first element, which is very obvious because the array initially was increasing. So if we rotate it, the last element or the element from the later half will obviously be greater than all the element on the lower half. And when I bring this part on the front, then all the elements which were lower will go to the other part of the pivot, right? So every element on the bigger elements came to the front and the smaller element went to the back. So every element after the pivot will of course be lower than the first element of the array, because the first was initially on the later side of the array, right? So this is the observation that will help us to find the pivot of the element. So the predicate will be, let's say our array was ARR. So ARR of I is greater than or equal to ARR of 0. So this is the predicate, and let's see how it happens or not. That's right. So 8 is, so our ARR of 0 is here 8, right? The first element. So is 8 greater than or equal to 8? Yes. Is 9 greater than or equal to 8? Yes. 10? Yes. 11? Yes. 12? Yes. Right. But as soon as we reach the pivot, that is where the predicate value changes. Is 1 less than greater than equal to 8? No. So from here all the predicate will be false till the end. So how we can use this predicate thing to eliminate the search space and apply binary search here? So like any binary search question, we'll have to find the mid. So mid in this case will be, let's say first mid. The first mid will be 11 plus 0 by 2. That will be equals to 5. So what is the that element 5? 1. So we see 1. So we'll apply. Is 1 greater than or equal to ARR of 0? No. That means we are on the right side of the array, right? That is on, we are on the right side of the array, and then we can say that every element on the right will also be false. So we can ignore that part of the array, and our pivot will be on the left, this part of this uh, uh, array, right? Now our low will be 0 only and our high will be mid. So mid will be 1. This is the fifth element. Now we'll find the another uh, mid, then that will be 5 plus 0 by 2, that will be 2. So at index 2 we have 10. We will compare it with the first element. Is 10 greater than equal to 8? So yes, it is greater than equal to 8. So we can say that 10 is satisfying the predicate that it is greater than the first element, then all the element before 8 will also be on the first half, right? So we can ignore this part of the array, and then our new uh, low will be 2 and our mid will be whatever it was. Now we'll find new mid. So new mid will be 5 plus 2 by 2, that is 7 by 2, then it will be add to 3. So 3 we have 11. 11 again satisfies the predicate, so it will all the elements lower than this will also satisfy the predicate. Our low will move again. Similarly, now our mid will be 5 plus 3 by 2, this will come out to be 8, and this is the 8th position. So this is also satisfying the predicate, so all the elements lower than this will also satisfy the element. So now my search space is only this. Now we'll find the mid. The mid will be, so my low will now coincide with the 5, right? And then if as soon as it reaches low equals to high, we'll see that we have found our predicate. So this is the whole logic of finding the predicate, finding the pivot index from where the array was rotated. So once you have this pivot index, you know, like this part is increasing, this part is increasing, and you can simply apply binary search on this part. So this is how you will use binary search to solve this question. Now let's say let's talk about the time complexity of this approach. So we are using binary search to find the pivot element, so that will take log of n time. Log of n is the time complexity of binary search, and once we are using log of n to find the pivot, and then after we have found the pivot, we'll use again binary search to search in which part our target element lies, right? So this is that will again take log of n time. So this is actually a 2 of log n algorithm, and on big O notation it will be log of n only. So let's see the code now. So this is the code, and let me give you a walkthrough of the code, and then we'll see the another approach as well. Right. So here our input was nums array and the target that we need to found. So this is the first check, like if there is only one element in the array, and then we'll just uh, compare it with the target that we are trying to find, and if it is equal, we'll return 0. Otherwise, we'll return -1. Now, what we are doing here is we are finding the pivot of the array from where the array was rotated. So this is the method which actually, let me zoom it out a bit. Yeah, so this is the uh, method which will actually return you the pivot. So we are actually taking the low, then we are finding the high, and this algorithm will run as long as the low is greater than high. We are finding the mid, and then we are checking what is the like if we have this thing 1 2 sorry 4 5 6 7, then 1 2 3, then what is the property of the pivot? Like the element before it should be greater than that. Or we can also say the if we are examining any element, and if the element after it is lower than this, then this one, the later element is the pivot. So same thing we are trying to find here. So this is the check that it should not cross the boundaries, and then ARR of mid, let's say our mid was this 7, this mid is greater than mid plus 1, that is 1, then this will be our pivot. So we'll simply return the mid plus 1. Else we will evaluate the predicate and eliminate our search space. So here we are checking if this is less than ARR of low. So if this thing would have been less than this, then we would have inferred that we are actually on the later part of the array, right? And then we have to uh, decrease our search space. Our pivot would be on the left side, so we are decreasing the mid, else we are increasing the mid. This is the same logic of actually comparing it with the first element. And then once we have found our pivot element, then we can apply the binary search. So here if you see, after like we have found the pivot here, then it can happen the pivot is at the 0th index, that means the array was not rotated at all. Then I have used here simple arrays.binary search method of Java, which actually returns the index of the element it found, otherwise returns a negative value if it is not found. So answer, I have, if pivot is 0, that means the array was not rotated, and then I have simply called it with the initial element and the last element and the target that we are finding and the array that we need to pass, and then this will give me 0 answer. So I'm storing it in a variable answer. Now here is the, now if pivot was not 0, that means we, their array was rotated, right? So then we are comparing it, the target, with nums of 0. So if target is less than nums of 0, for example, if it was 4, 5, 6, 7, 1, 2, 3, and then we are finding the, let's say we have to find the target as 2, right? So if target was less than nums of 0, we can say that it is on the later half of the array. So we need to apply binary search on the element right of the pivot. So I have passed pivot as the initial index and nums.left as the last index to actually find the element, else we are on the left side of the pivot. So this is from 0 to pivot plus 1 we have applied. And if we, and this method arrays.binary search, it returns a negative value if it is not able to find the element. So if it is less than 0, we'll simply return -1, otherwise we'll return the answer, right? So this is how you can use binary search to find the pivot element first and then apply binary search to get the answer. So we, as we already discussed, the time complexity of this approach was log of n, but we are actually, if you see here, we are using binary search twice, once for finding the pivot element and once for applying binary search on any of the part, right? So we can actually optimize this code a bit so that we can do it in one pass. Now let's see that approach. So this is the code of that approach, and I'll explain you in the brief what is the idea of this approach, right? So what we are essentially doing here is, I'll explain you with the data set 4, 5, 6, 7, 0, 1, 2, and we are trying to find the target, which is 0, right? So what we are essentially doing here is, we are first finding the mid. So mid in this case would be 0, 1, 2, 3, 4, 5, 6. Mid will be 6 plus 0 by 2, 3, seventh element. And then we are simply checking if this is equal to our target. So this is not equal to our target. Then now we need to make a decision. Should we search on the left part or should we search on the right part? Sorry. So how to make that decision? So first step would be check where the current element is. It is on the first part or it is on the second part. So I'll just draw this boundary here, which will tell me whether if I'm at the first part or the second part. So how we can check if we are in the first part of the array or on the second part of the array? So it's simple, right? We'll just check it with the array of 0. So if this is greater than or equal to the array of 0, then we are on the first part, else we are on not on the second part. So this is what our code is doing. We have defined our low, we have defined our high, and then we are finding the mid, and then we are checking if the mid is equals to target. If mid is not equal to, which is equal to target, we are simply returning mid. Otherwise, we are then checking whether we are in the first part or we are in the second part. So here 6 plus 0 by 2 was 3. 3 is our middle element. 7 is not equal to target. Is 7 greater than 4? Yes. So we can say that it is in the first part. So this way we will find which part of our current element is. Now we need to actually adjust our low and high accordingly. So once I have found out like I am currently at which part, the second I need to check where the target element is. So target element is 0. We'll compare it with the first element. Is 0 greater than equal to 4? No. Then we can say that 0 is on the later part. So our mid was this, our low was this, our high was this. So we need to search on the later part. So what we need to actually change? We need to change our mid. So we'll change our mid to low to mid plus 1. So our new low will be here and then we'll continue our search on this part. Right. So this is how this element, this thing works. So after the first iteration, my low will be 0, 4, my high will be 6. and then let's try to find out the mid. So it will be 6 plus 4 by 2, that will be 5. So 5 is our mid. Will Is mid equal to target? No, mid is not equal to target. So we will check it which half this thing is like. So is 1 greater than 4? No. So we know that this is on the right side of the array. So we need to so once we have found out which part of the array, then we need to check where our target lies. So we know that we are on the second half of the array, and then now we will check where our target is. So our target, when we'll check 0, this is greater than 4, then this is also on the second half. So we need to continue our search on the second half only. So then now we will check whether our element, this is now a simple binary search logic only. If we have found that both the target and the mid is current element mid is on the same part, then our the reduction of search space will follow the simple binary search logic only. We'll compare the mid with target. So if mid greater than 0, yes, if mid is greater than 0, then we need to adjust our high. So our high will then be mid minus 1. So high will collide here, and then in the next step the mid will be this element only, and this will return 0. So this is how this particular algorithm is working, and then let me just give a code walkthrough briefly. So here we are, what we are doing, we are finding low, we are finding high. As long as low is less than equal to high, we are finding mid again. We are checking if mid is equal to target. If it was, we would have returned. If it is not, then we are checking which half we are currently is. So if nums of mid is greater than nums of 0, we are in the first part. Right, so we are in the first part, so this whole code is for the first part. Else we are on the second part, so this whole part is for the second part. So in when we are in the first part, we'll then simply check where our target element is. If our target is also greater than the first element, then that means both the target and the mid are on the same part. Then we'll just apply the simple binary search logic of checking which if it is greater than mid is greater than target or not, and then adjust our low and high pointers accordingly. Else, if we are in the first part but our target is in the other part, then we have to modify the low pointer. So this is how we are reducing the search space. And then the next part is, if target is now this is the half when our mid is in the second part, right? So when our mid is in the second part, we'll simply check if our target is also on second part or not. So if our target is on the second part, if it is less than nums of 0, this is the condition to check now where our target is, whether on the first part or on the second part. So if target is on the second part, then we'll just see if both the target and mid is on the second part. So if both of them on the second part, this will follow the normal binary search logic of comparing it with the mid. Else, if we find that we are on the second part, but our target is on the first part, then we have to adjust our high pointer. So this is how this binary search logic is working, and this code I find better than the earlier approach because you don't have to run it twice. But this can be quite complicated to read. So in the interviews you can actually tell the pivot approach as well. It won't harm you. But if you will tell this approach, then the interviewer might have a good impression of you, that okay, you care about performance and good writing optimal code, right? So yeah, this is how this question can be solved, and you can find the code link in the description. And please, if you are new to this channel, please like, share and subscribe, and just mention in the comments below what else would you like me to upload. And stay safe. Bye bye. Thank you.